Student performs an experiment to determine the specific heat capacity of a metal. Student places a cube of metal in boiling water, so its temperature will be 100 degrees Celsius. The student places the metal cube into a calorimeter that contains water and records the highest temperature of the water, a data table, and a diagram of the thermometer at the highest temperature shown. Okay, so here's your reading question here. If I take a look at that, so the highest temperature of the water, remember we go one digit beyond we can accurately measure, so 35, 36, 37, 38. Looks kind of right there in the middle, so 38.5 degrees Celsius, maybe 38.4. Again, just it kind of depends on how you read that. I'm reading it as smack dab in the middle, so I don't see any reason to go any different than that. So, okay, cool. Particle of a representation of water and molecules in the diagram before and after the middle cube is added. Length of the arrows represents the speed. Okay, so if the initial temperature of the water here is 25, metal cube is in there, heat transfers from hot to cold, so temperature of the water is going to go up, which means that the molecular speed is going to increase. So we're just going to draw these a little bit longer. Okay, pretty straightforward question, especially in terms of molecular movement of molecules when we're talking about temperature. So, okay. All right, so assuming the metal transfers 2940 joules of thermal energy to the water, indicate the specific heat of the metal. Okay. I need to think about this one for a second. Let's look at the information that we have in the problem. So again, another Q equals MC delta T here. So transfers 2940, the metal transfers the heat. So if that's the case, it's losing heat, right? It's losing that energy. So this value is negative, so negative 2940. I'm probably giving the mass of the metal somewhere in here. 98.1. Okay, I can do that. So 98.1. It wants to know the specific heat, so we're solving for C. Our initial temperature is 100. And our final temperature. Now, I'm going to make an assumption here based on the information of the problem. It does say here that this is the highest temperature shown. And so what that tells me is with the highest temperature, the H2O and the metal are at thermal equilibrium. Okay, meaning that the temperature of both is the same. So this is not only the final temperature or highest temperature of the water, it's also the highest temperature of the metal as well. So that's going to be my TF is 38.5. And now what I can do is go through and algebraically solve for my specific heat. And that makes sense because you're going to end up with two negative values here. And so that tells you that C is going to be positive when we go through and divide this out. So do a little bit of math here. So negative 2040. I'm going to divide that by 98.1. Okay, and then what I get here, I'm just going to kind of give some information myself. So negative 29.96, 38.5 divided by 100, negative 61.5. So if I take those two values, I get a specific heat of 4.87 joules per gram times degrees Celsius. Okay. Okay, makes sense. Again, metals have very low specific heat, so I'm on board with that. So, in the second experiment, a 2940 joules of thermal energy is transferred from 98.1 grams of aluminum, which has a specific heat capacity that's different. Okay, so we're looking at two different chemicals with two different specific heat capacities. And this is explain how the magnitude of the temperature change of the aluminum compares with the magnitude of the temperature change of the metal in the original experiment. Well, the specific heat capacity here is greater, right? Means that it requires more energy to change the temperature. So that implies to me that the magnitude of the temperature change of aluminum is going to be lower than that. If the same amount of thermal energy is transferred and the specific heat of aluminum is greater, it's going to require more energy for the aluminum to change 1 gram of the material 1 degree Celsius. And so as a result, we end up with the fact that the temperature change of aluminum is going to be lower than that of the temperature change of here. And again, that has to do with the specific heat of aluminum being higher than, let me scroll that down a little bit because I got a little more room. Oh, yeah, plenty of room. Aluminum is higher than that of the unknown metal. Okay, again, kind of abbreviating my free responses here, but I want to try to get through a reasonable amount of time. Again, pretty straightforward question here. I think that there's a little bit of difficulty here because I feel like a lot of students may not necessarily get that because that is the final temperature of the water, it is the same as the final temperature of the metal as well. When thermal equilibrium is reached, the two temperatures equal one another. And so as a result, the final temperature of the water would be the same as the final temperature of the metal here. So, okay, question 4 is taken care of. Let's go on to question 5.